little bit of preliminary remarks real fast. Does everyone know what a function is, mathematical function, for the most part? And everyone knows what a variable is? Okay. Because I tried to write this paper on functions, and quite truthfully, it's hard to put mathematics in words and not symbols, so I tried. So we'll see how it goes. All right, you ready to start?
Mm-hmm.
Okay. Running?
Mm-hmm.
Okay. Hello and welcome. My name is Carl Campbell, and I'm here today to inform you on a specific mathematical fact. Mathematics has always been one of my favorite hobbies, I would say, in general. And I always found it to be one of those things that I do when I'm bored. Not a lot of people do that when they're bored, but I was. I always found that anything that I do in mathematics, everything that I learn, there's always something new to discover. It's a growing and changing world, and it will always grow and change. And whatever you learn in math, there's always something to go on top of what you've already learned. Whether you're studying calculus or statistics or abstract algebra, topological spaces, or whatever you study. But there's always been one term in mathematics that has always intrigued me, and that was and it's a very broad term, and it was the term function. And in general, functions are used throughout all of mathematics, and all mathematical branches have their own ways of looking at and representing a function differently. Functions are represented differently in statistics, for example, probability density functions, or in calculus where you're trying to take a derivative or integrate a function. And in any branch of math that you study, you're going to come across a function one time or another in your life, and we deal with functions every day. We just don't realize it most of the time. So functions explain essentially, they're everywhere. They're in engineering, sciences, computer science, and even life. Functions explain bodily operations that happen throughout our bodies, everything. So a function is a relation between a specific set of input values mapping to a specific set of output values, into which each input value that you have must map to exactly one output. To make this more clear, let me explain what a relation is. A relation is when you have one input value or multiple input values mapping to more than one output. You may have one input mapping to more than one output or multiple outputs. And a function is just a special case of a relation. It's just the fact that I have one input, and every input in a specific set maps to only one output, and it has to be one specific output. It cannot be multiple. And today I actually want to give you all a little bit of a verbal proof. I want to propose today that all that a function really is a deformation of the real number line. And the real number line, right, contains all numbers, all integers, all natural numbers, rational numbers, irrational numbers. It contains everything except for complex numbers. And what I'm proposing here today is that the real number line essentially deforms or forms into the shape of whatever graph you're trying to function, whatever function you're trying to graph. So imagine that you have a variable x, and it's a variable, And if x is a variable, then its function value has to be a number, because a variable is a placeholder for a number. So the function itself has to be a number. And let's experiment and think, what are all ordered pairs? All ordered pairs of numbers that are graphed as points on a Cartesian coordinate plane consist of two numbers, in general, two numbers. They would be an input value x and an output value f of x, where f of x is your function value, in which case both values are numbers. So therefore, the ordered pair itself consists of numbers, and the point on the graph in which the function in which you're trying to graph will also be a number. So if every ordered pair consists of numbers, and a function value itself is a number, then the graph of the function is just an infinite set of numbers. And so if a graph is merely an infinite set of points that correspond to numbers, then the number line, the real number line, is essentially shaping to the graph of the function. Because if you pick any point on a function's graph, it's going to map to a set of numbers. So it makes sense to say that any function you try to graph, any function, is a number. And thus, the number line is deforming to fit the shape of the function. For instance, y is equal to x squared is an example of a function. It creates a parabola, a U-shaped graph. And in specific, there are 3 points that you will typically use to graph a parabola: a vertex, an x, and a y-intercept. And when you get through graphing those points, you have to connect them with lines to form your U. But the interesting part is, any point on those lines corresponds to a pair of numbers. So essentially, you can think about it as the real number line is deforming itself, forming into that U shape. And keep in mind that this parabola will go up on both sides, negative or positive, to positive infinity. And if you have y is equal to x cubed, it will go to positive infinity and down to negative infinity. So you're going to have an infinite amount of points, and the real number line goes to the right positive values, to the left negative values, and they both go to infinity. So if that holds true, then any function that you try to graph, any point on that function corresponds to a number, and the real number line is essentially just shaping itself to fit the shape of that function of choice. And that is why a function is a deformation of the real number line. And that is basically all that I have to say today. Thank you for taking your time and listening to this speech. And thank you very much.
Thank you.